The other big part of organic chemistry is how the chemicals react. And this is by far the bigger portion of organic chemistry relative to nomenclature. Knowing how to name things is definitely the first step. But the reactivity is just crazy because you have to know what to do with the chemicals when you have them and how to make them if you don't have them. So we're just going to look a little bit at some general patterns, all right? And in the actual organic chemistry class, then you'll start seeing more examples and you can get into more detail. So kind of bear with me here while we go through some typical examples of how organic chemistry works. An addition reaction is what happens when you have an unsaturated alkene and you add a diatomic molecule to it. And the double bond breaks and you end up with single bonds. So here's an example of what this means. A double bond, or a triple bond for that matter, is considered unsaturated, which means that you have more spots that you can put atoms if you break apart the double bond. Like you can break apart some of the carbon-carbon bonds. So if you add bromine, for example, then one bromine atom goes to the left carbon and one to the right. You can see how they basically separate and go where the double bond was. So your ethene compound on the left reacts with bromine to make 1,2-dibromoethane, which is an alkyl halide. Now, if you added hydrogen, H2, to the ethene, you would turn it into just ethane. You're turning an alkene to an alkane. If it was HBr, then one hydrogen would go to the left and one bromine would go to the right. So you'd end up with something like 1-bromoethane. You could add water. You'd have an H and an OH. It's pretty cool. Those double bonds are actually pretty reactive, and adding a diatomic to it means you can break it up.
Molecules of bromine gas undergo an addition reaction with the carbon-carbon double bonds in bacon fat, causing consumption of the bromine gas.
This is an example of adding bromine to a double bond and then breaking it up to make a dibromo. This is bacon fat, which is pretty disgusting. But anyway, you can break apart the fat in the bacon and the bromine is used up. Bromine has that kind of dark yellow kind of looking color when it's in the gas form, and then as it reacts, it does different things. So, oh joy, the fun you can have with chemistry.
Atoms of hydrogen gas undergo an addition reaction with the carbon-carbon double bonds of propene, changing the molecule into propane.
You can easily turn alkenes into alkanes by adding just hydrogen. So this was turning propene to propane, all right, which is really simple. Like I've kind of mentioned earlier quickly, an alkene is much more reactive than an alkane. Alkanes usually are just good fuels, more or less, but alkenes, you can do lots of things. You can add diatomics across them, stuff like that. Fats can be hydrogenated with hydrogen, H2, all right? And sometimes that's good. It makes them easier to store or not quite as readily to break down, stuff like that. And this leads into hydrogenated fats. And if you look on the sides of some containers, you end up with partially hydrogenated oils, all right? That means that hydrogen was added. They're trying to break apart the unsaturated fats into saturated fats, and there's reasons why they want to store it. A lot of times, though, the partially hydrogenated fats are really bad for us, and so you should be careful of them. But anyway, this is the process. They're trying to add enough hydrogen to make the double bonds break up into single bonds. I am reluctant to think that any of these processes are 100%. So I would be very, very careful if you were going to consume hydrogenated oils. I don't think that they're totally free of some of the bad things in them, but that's my personal theory.
In the substitution reaction of glycerol with nitric acid, hydrogen atoms on the glycerol are replaced by the nitro group to produce nitroglycerin and water.
Nitroglycerin is essentially triol glycerin with a nitro group, and if you add nitric acid to it, it'll make it. It's pretty unstable, causes lots of cool explosives. This is an example of a substitution reaction where you're taking some more exciting pieces and basically swapping them out. So the NO2 basically swaps out one of the hydrogens and one of the OHs, so you end up with this nitro group, and again, that's pretty unstable. There's a lot to substitution substitution reactions. And again, in the organic chemistry year-long course, you'll go into a lot more about substitution reactions.
In the reaction of 1-propanol and sulfuric acid, a hydroxyl fragment is eliminated from the 1-propanol to form propene.
Earlier I said how alcohols are also very reactive, and this is an example of what this is. If you have an alcohol and you accidentally or intentionally add a little bit of acid to it, acids act as a catalyst, so it means they react with a chemical, but they're also regenerated at the end, so they can react more. But anyway, the acid will actually cause water to be kicked out of the alcohol, and an alkene forms in its place. So you're essentially turning then these kind of alcohols into alkenes, which is kind of cool and stuff, but it is pretty interesting. When we ship our waste, we have to make sure that they are certainly not acidic, because a lot of times with organic chemicals, you can make wild reactions happen. This is called an elimination reaction. You're essentially eliminating the OH of the alcohol and another hydrogen to the adjacent carbon to make the double bond. And again, you have to have H plus as a catalyst to get this started. We'll talk more about catalysts towards the end of Chem 222.